Today it's my pleasure to introduce Nicolò Pinciroli. Nicolò is a grad student at the Polytechnic of Milan in Italy, and he is visiting for this month, working with us on a couple of AstroAI projects. Nicolò is actually a computer scientist more than an astrophysicist, but he's been working on topics of gravitational lensing, exploration of machine learning algorithms for gravitational lensing. And he's been working on representation learning for X-ray data sets and multimodality, combining X-ray data sets in different modalities and also with text using LLM. So today he's going to tell us about AI and complex networks in multimodal X-ray astrophysics. This time I will sit at the back so that if you do have questions during the talk, just raise your hand and I can pass you the mic. Nicolò, the floor is yours. Thank you.
Thank you. So nice to meet you. My name is Nicolò Pinciroli, and Rafael already gave the introduction. So today's presentation is about artificial intelligence and complex networks for multimodal X-ray astrophysics. This presentation is divided in three parts. That is, clustering Chandra X-ray spectra. So we have this Chandra spectra. We want to cluster them, and how can we do this? Well, we need the spectra, of course, and we will use autoencoders to compress them into a smaller representation, a compressed representation that summarizes the main properties of the spectra. Then we will use clustering algorithms in order to actually cluster these smaller compressed representations of the spectra. And then we will use symbolic regression to understand if the latent space has some physical meaning, is correlated with some physical meaning. The second part of the presentation will actually use multimodal data. And in particular, what I will present is the alignment between X-ray event files, so the data from event files, and scientific texts taken from scientific papers. For doing so, we can use the ADS dataset and, of course, the Chandra event files. How can we address this kind of problem? We can use, for example, contrastive learning that tries to put both the data from both modalities in a common shared space with the dimension we choose. Finally, the final part of this presentation focuses on trying to discover some patterns in multimodal data again. Now, I will focus on high variability X-ray sources, which are particularly interesting for astrophysics, and I will try to use complex networks that I will introduce later. They're not part of artificial intelligence, actually, to discover some relevant patterns in the data. Okay, to start, I would like to present you the pipeline for clustering Chandra spectra. So first of all, we have this Chandra spectra. We know that they have different lengths, different numbers of points. So the first step is pre-processing this spectra so that they have the same, all of them are represented in a uniform way. Then we can use an autoencoder to take these spectra and to compress them into a so-called embedding space. So we want to obtain a compressed representation of all the spectra, and then we can cluster the compressed representations in 8 classes or 2 classes, or well, we can choose the classes of interest and see if they are placed in different clusters in the space. Finally, we also want to see if the latent space or embedding space has some physical interpretation that the autoencoder could extract autonomously from the spectra. To do so, we use tabular data that the autoencoder has not seen before, and we will try to see if the latent dimensions are correlated with expressions that will use physical variables. I will describe this in more detail in a few minutes. Okay, the first phase, as I was mentioning, is pre-processing. So spectra have a variable number of points. In this case, I will focus on using, I will use only 400 points to represent all the spectra. Some of them will have fewer points, some of them will have more points. The idea is that with 400 points, I can describe the entire spectra, and I have the same energies for all the spectra. What is different is the energy values. Now, what we also know about the spectra is that the fluxes depend on distances, and we don't want this to be a bias in our case, because we don't want to classify or cluster our sources based on distance. We are more interested in the shape of the spectra. So after resampling the spectra, we also rescale them in the range 0, 1, so that the autoencoder will focus on the shape of the spectra rather than on the absolute flux values. And then we need to introduce the classes we will use. So we have 8 classes: AGNs, cataclysmic variables, high mass stars, high mass X-ray binaries, low mass stars, low mass X-ray binaries, neutron stars, and young stellar objects. We will use these 8 classes for the first clustering experiment, and then we will focus on 2 classes for the second clustering experiment. In the second experiment, we will have AGNs as one class, and high mass X-ray binaries, low mass X-ray binaries, and neutron stars in the other class, because all of them contain, well, I would say, stellar size compact objects. And finally, we will focus on the latent space for the AGNs and see if there is some physical meaning in this latent space. How can we do this? How can we cluster data? Well, the first step is training an autoencoder. So what an autoencoder does is taking an input that in this case is the pre-processed spectrum, and then it tries to reconstruct the input in the best possible way, but it tries to do this by compressing the information in a very small space. In this case, we have 400 points for each spectrum, and we try to compress all of this information using only 8 points. 8 values that are represented as a vector. And these vectors are the latent vectors. Now, the reconstructed spectrum then will need to be as similar as possible to the pre-processed spectrum, and this means that the latent representations of the spectra will contain the most important information about the spectra. We need to evaluate how good is the reconstruction, and to do so, we can compute a reconstruction error that in this case is the mean absolute error. And what we notice is that both on the train and on the validation set that contain sources that are not labeled, for which we don't know the class actually, for both of them, we have a train loss that converges, and the same applies to the validation loss, and it is quite low, so 4 times 10 to the minus 2, where the scale is between 0 and 1 for this spectrum. Now, what we obtain when we apply the transformer autoencoder, so the final reconstruction is the red curve you can see here. So since we are compressing the initial information, we have a reconstructed spectrum that is a smoothed version of the original spectrum, which actually makes some sense, even because the original spectrum also has some error bars associated with it, which are not considered in this work. We will consider them in the future. Now, when we try to cluster this spectra, exploiting the compressed representations, we can use several algorithms to do this. The most effective one in this case is Gaussian mixture models. And as you can see, we can compute a sort of confusion matrix that is called contingency matrix in this case. So on the y-axis, we have the ground truth classes, while on the x-axis, we have the clusters. Of course, if we have the clusters, they are identified by IDs. They are not identified by class names. So we need to associate clusters with class names. To do so, we can just maximize the sum of the elements on the diagonal of this matrix, that is the trace of this matrix. What is the meaning of these values in this matrix? Well, the elements on the diagonal, so the sum of the elements on the diagonal, is just the balanced accuracy, because each row is rescaled, so the sum of the values for each row is 1. And in this way, each class has the same weight independently on the number of samples in that class. And this experiment was performed on the test set that is the only one for which we have the labels for all the observations, so the classes for all the observations. Now we can extend this experiment to the two classes case. So AGNs on one side and high mass X-ray binaries, low mass X-ray binaries, and neutron stars in the other on the other side. In this case, the problem is clearly simpler because we have only two classes. And in this case, the balanced accuracy obtained with the best clustering algorithm we used in this case is about 70%. Now, the next step is trying to understand for AGNs whether there is a meaning associated with the values in the embedded representation. So how can we do this? Well, we can use, for example, symbolic regression. For those of you that are not familiar with symbolic regression, the principle is very simple. So we have some physical variables. Of course, we have the values associated with these variables. And we will try to create physical formulas, in this case, for example, ratios between fluxes. And we will see if these physical formulas are well correlated with the latent space dimensions, so the compressed representation. And what we can see is that the correlation is quite high, for example, for the first embedding dimension, and we have Pearson correlation index of 0.744. The best is 1. This is a positive correlation. The worst is 0 for positive correlations. For negative correlations, we would have -1 as the best one. So there is a strong or moderate to strong positive correlation between the ratio between the flux in the hard band and the flux in the broadband and L1. And we can observe some correlations also in the case of other variables, and they have some physical meaning. Actually, it looks like they have some physical meaning. Now, this is just unimodal experiment, so we are using only one modality, so only the spectra. What can we do instead if we use multiple modalities? So part of the future work will be integrating also the spectra and using the spectra as one of the possible modalities. I haven't done this yet, but we have just submitted a paper with Rappel and the remaining part of the AstroAI group that focuses on multimodal data formed by texts that are summarized by LLMs and event files. Then there is a tool and there is a paper about this that is PPAD that tries to extract the light curves from the event files that contain a lot of other information. However, the goal of this the second part of the work is learning from multiple modalities. So taking the compressed representations from both modalities in this case, so text embeddings and data embeddings, and try to align them into a shared space to see if we can, for example, perform regression in this shared space, and if we can obtain better results than what we would obtain with a single modality. And the same, we will do the same for anomaly detection, for example. Okay, so the structure of this neural network is quite simple. So we have two fully connected networks to compress the text embeddings into 64 dimensions, that is the dimension we chose for the shared space, and to enlarge the data embeddings to 64 dimensions as well, so that they have the same number of dimensions. Then, and this is something strange for contrastive learning, but it works for this specific application, we add a final fully connected neural network that uses both modalities at the same time to position the points into the shared space. With this final part, we cannot perform, for example, cross-modal retrieval. So, for example, if we have only a text, we cannot retrieve the closest event files having only the text. However, what we can do is what we will have is a compressed representation that puts the texts and the event files information together. How can we train this kind of network? Well, we can use a loss that is formed by a contrastive loss, that is the infancy loss, and a regularization part. The regularization part aims at preserving the distances between data and other data and between texts and other texts from the original spaces that are this one, the original embeddings, to the shared space. And as you can see, we have a train and a validation set. And as you can see, it converges. It is able to align this information. Now, what if we try to perform regression on the final shared space? So first of all, if we use only one of the two modalities, for example, only text or only data in this case, so only event files in this case, what we observe is that texts are better than data for hardness ratios, for example, and also for the variability probability. And sorry, not for the variability probability, sorry, the opposite. Data are better for the hardness ratios, for the variability probability, but they are worse for the flux significance. These values are, again, mean absolute error, so of course, lower values are better. And as we expect, the information about the hardness ratios are inside the data, but not necessarily inside the text. Well, if we use both modalities, so we use the shared space, what we obtain is that the mean absolute error is always better or equal than the best of the two modalities. And there is quite a significant improvement, especially for the hardness ratios. We can also check whether this shared space contains interesting information in terms of useful for anomaly detection. And indeed, we can find anomalous points in the shared representation. And these anomalous points are actually rare sources. For example, we have a ULX, a cataclysmic variable, or in general, they are not necessarily rare sources, as in the case of YSO, but they have some peculiar properties that make them anomalous. Now, the final part of this research focuses on highly variable X-ray sources that are particularly interesting for some astrophysicists. And for example, if we consider ULXs, we can have pulsating ULXs that are quite rare and very rare, I would say, and very variable as well. So now let's focus on a subset of this X-ray data. We have around 4,500 highly variable sources in this data set. And let's use again scientific texts and event files. Now, the idea is to see whether there are patterns in this data, and we can use a tool called complex networks to see if we can find these patterns. So complex networks are just graphs, basically, but in addition to graphs, they show a non-trivial topology, so some special topology, which is associated with well-studied properties. And there are many studies on complex networks to analyze their behavior in a well-established way, so with well-studied metrics. So the pipeline in this case is quite similar, apparently, to the previous one. So again, we have the text embeddings and the data embeddings. Now we have the text embeddings that are just vectors, and we can compute the cosine similarity between couples of text embeddings, of course. Now we can build then a similarity matrix in which each cell represents the cosine similarity between a couple of text embeddings. And we can do the same for data embeddings. Now, this similarity matrix will have these cells, and high values in these cells will correspond to a higher similarity. Now, how can we put this information together? Well, we can take, for example, the average of the similarity matrices, and now we obtain a final similarity matrix that is the average of these similarity matrices. From a similarity matrix, we can devise a graph. In this case, it is an undirected graph, and it is undirected because the similarity between an observation A and an observation B is the same as the similarity between B and A. Okay, so it is not directed. Now, we have a graph with nodes that correspond to observations and edges that correspond to the similarity between couples of observations. So we have edges between every pair of observations. Now, we are interested in knowing which ones are similar to each other, because in this way, we can find the ones that are not similar to many other observations, and we can say they have an anomalous behavior, for example. How can we do this? Well, now we take our similarity matrix, and we say that we set a threshold, and we say that all the values above that threshold are set to 1. So this means the two observations are similar to each other. The values below the threshold are set to 0, which means we remove the edge inside the graph. Now, what happens if we consider different threshold values? Well, first of all, we need to introduce the concept of degree. So the degree in a graph is the number of edges connected with a node. In this case, since a node is an observation, it represents the number of observations that are similar to a given observation. So if a node that is an observation has a very high degree, it means that it is similar to many other observations. If it has a low degree instead, it means it is different than other observations, so it is an anomalous observation. Now, we can represent this network using these plots, and we can identify two regions. So the colors here correspond to different degrees. So brighter colors like yellow correspond to a high degree, while the colors that go towards blue correspond to a low degree. Independently on the threshold, we can see we have a core that contains a dense core that contains similar observations with a high degree, and then a periphery that instead contains observations that are not very similar to each other and not very similar to the core. And this kind of structure, this kind of topology is called core periphery structure. And what we notice is that in the dense core, let's focus now on tau equal to 0.7, so threshold equal to 0.7. What we notice is that inside the dense core, we have connections between almost all the nodes. So all of them are similar to each other. Most of them are similar to each other. And this concept is called density. This thing is called density. So the density is the number of edges we actually have with respect to the total number of possible edges if everything is connected, and it is close to 1. While for the periphery, this is almost 0. So we have two very different regions. Now, this information can be also represented with this plot. So here we have the degrees. Here we have the histograms with these degrees. So what we can observe is that independently on the threshold, we have two distinct regions, one with low degrees and the other one instead with high degrees. So this is a bimodal distribution that again underlines the presence of a core periphery structure. And what we can also notice is that some classes have usually high degrees. So this threshold is set on for a threshold of 0.7. This set manually, can be done automatically probably, but anyway, we can notice that, for example, YSOs and YSOs candidates have similar properties. That is good, it makes sense. I expect many YSO candidates to be actually YSOs. And what we also notice is that X ray sources, these are generic X-ray sources, have a percentage of observations with a high degree of 75%. That is very, very close to the percentage we would obtain if we consider all the sources, which makes sense because maybe these unknown X-ray sources are distributed as the object types are distributed as the known ones. And interestingly, for ULXs, for example, we have only 9 ULXs, actually, 9 highly variable ULXs in the data set. And what we observe is that all of them have a low degree, which means all of them are considered anomalous with respect to the remaining part of the data, which makes sense because they have some anomalous properties. So to conclude, what this presentation has shown is that transformer-based autoencoders are effective for reconstructing spectra, of course, a smoothed version of the spectra, that we can perform clustering if we use these small latent vectors, and that this latent space, in this case, has some physical meaning, even if the autoencoder did not know about physics. Then, this presentation has also shown that aligning multimodal data is beneficial for regression and for anomaly detection, and that we can use complex networks to analyze the distribution of observations. So we can find anomalous sources, we can find particular topologies, for example, in this case, a core periphery topology. Thank you for your attention. This is all.
But first of all, I was just told that a photo of the audience will do instead of signature. So unless I have opposition from the public, I'm about to take a photo of you. Beautiful. All right, thank you.
There's the people upstairs.
Oh, yeah, well, those guys are accounted for. So this accounts list. Anyway, so do you have a question?
Yeah.
Great talk. Could you go back to one of the very first slides where you showed the spectrum and how you were sampling,
Yes.
like all the spectra?
This one?
Go back earlier, actually.
This one?
Yes, this
Yes.
right here. So you're rescaling the fluxes because they depend on distance, not
Yes.
physics properties.
This is not rescaled, actually. This is just resampled, but not rescaled.
Sure. But what about red shifting? So cosmological red shifting of spectra, you could have the exact same source, but the spectrum changes simply because, because you said you sampled the same energies, right?
Yes.
So if you have the same source, but it's at a different distance,
Mhm.
and the locations of certain spectral lines change because you've shifted it.
Mhm. Yes, so in that case, well, in this case, I consider 400 points. That should be enough to capture all the spectral lines, hopefully. But if I understand your question, well, in that case, the same source will actually have 2 different spectra. This is true. But we have, I think, 50,000 samples. So I think that even these differences in the spectra for the same source they will be considered example of the same class, for example. Hopefully they will be considered similar spectra anyway. I don't know if I answered your question actually.
Yeah,
Maybe.
and
Yeah, okay.
I had like a related one, sorry if I could. It relates to the question of the spectral lines. So for a lot of X-ray sources, with harder energies or hotter temperatures, there was a line at 6.7 keV, an iron line complex that can be very bright and has a lot of good physical diagnostics. So you sample using 4 points with a log scale, meaning at 6.7 keV, you're sampling coarser.
Yes.
So I'm just wondering if that region is well sampled, because it could say a lot about certain types of sources.
Well, it is not sampled as well as the low energies region, but I think for this application with autoencoder, since the autoencoder compresses the spectrum, so we have a smoothed version of the spectrum, these lines might not be captured anyway, independently on the fact that we capture them in we capture them during resampling. So I think this autoencoder might be good for seeing the overall shape of the spectrum. So I had other plots, but I didn't have time to show them, in which we can see that, for example, the same clusters, a certain cluster will have a sort of average behavior, and then some deviation around this behavior. And I think that for the lines you are talking about, this might be captured by this variability in the spectra, in the spectra that are being reconstructed. But I mean, these lines are probably not captured in this representation, especially if they are quite rare for a certain class, or in general in the entire data set.
Thanks.
Yes.
There's one question here.
Yes.
Sorry, I have two very basic questions about autoencoders. So the first thing is, if you go to the reconstruction of this exact plot.
This one?
Yes, so for example, the very last point over there, you're sort of missing it. And I'm assuming if you change the number of parameters in the latent space, it starts capturing and overfitting the curve, right?
Okay.
So if you increase the number of parameters in your latent space, it starts overfitting the curve at some point.
Yes.
So how do you find that balance?
How
In
do I
terms of
find?
how many latent space
Okay.
parameters?
So what I did in this case was, so I tried with several hyperparameters combinations. Well, some of them didn't make sense because they were more than the number of points I had, so it didn't make sense. But basically, I chose the ones that were better for the clustering, for the final 8 classes clustering. However, I have to say that for clustering, I didn't have a lot of variability given by the dimension of the embedding space. I tried with 8 dimensions, also 16, 32 dimensions, and probably even 128. I don't remember now. Yes.
So essentially, you go up to the point where you construct the similarity matrix, and you see where the trace is the best in some sense, right?
Yeah, for the last part, yes. In that case, yes. I use other kinds of data in that case. I don't use the spectral data. I use the event files data. But yes, if you use if you have an autoencoder that is that has a lot of that has with embedding vectors that are very big, the reconstruction will probably be better. I don't know if it actually captures the important information or just copies the initial spectrum, for example. So I don't know how effective it could be for clustering or for alignment, but yeah, it would capture more information, definitely.
I just have one more question. If you go to the co-periphery plots where you have the variation with tau,
This
can
one?
you remind me what tau is here?
It is the threshold. So you have the similarity matrix. The values in the cells of the similarity matrix indicate the similarity between couples of points, so couples of observations. I put the threshold so that above the threshold, I have a link. Below the threshold, I don't have a link. There is a
Thanks,
question.
Nicolò, that was a great talk. I have a question about the LLM. And how do you prepare your input data? Like how do you give it like a PDF or an image and it does some text recognition, or do you put in the HTML? Does it also extract information from the plots, for example?
So I actually used the embeddings that had already been prepared. So I didn't work on the first part in which I extract the information. I believe this is part of Rafael's work actually, but I believe that that they are extracted mostly from the text, so that it is a summary of the text.
Right. So we have the ADS database here. So we have papers, and we're lucky enough that the Chandra archive has associated papers to specific ops ideas. And so we use that association, and then because we also have identifiers for specific sources, we prompt the LLM by asking specific questions about the sources as described in the paper. So that allows us to make a one-to-one association between specific embeddings of summaries of the physical descriptions of the sources by the LLM. with the actual data embeddings, with the decoder that comes directly from the event files. Yeah. All right, any,
I think there was another question.
oh, sorry, there was another question.
Yeah.
Sorry.
Did you have a question?
Oh, access, yeah.
Same question, okay.
Go for it.
I have the exact same questions, I just wanted to know like which text corpus was used to train the ML?
Which text, what, sorry?
Which text corpus was used? But you just
Oh,
mentioned-
yeah, it's ADS. So ADS, we're lucky to have Alberto's team here with that has compiled all the text data. Yeah. Oops, sorry. Anyway. Any other questions, comments? Well, if not, let's thank Nicolò again.
Thank you.
And we will not miss next week because it's President's Day and the week after we'll continue. Thank you so much.